4. Measuring distances. This is using triangulation and parallax. To measure the distance to a faraway object or star, we use triangulation, or what's called the parallax technique. Triangulation is based on the geometry of a triangle. To measure the distance to a star, we need to measure from 2 different points. We need to know the distance between these 2 different points. This is called our baseline. From each of these points, we measure the angle to the star. Angle observations, again, are made from these 2 separate locations. We then use a scale diagram or trigonometry to calculate the distance. So we can use trigonometry or math to calculate the distance this star is above the ground. Parallax. An example of parallax is in chemistry. And we're going to talk about it in relation to stars, but I thought that this might be a good example for stars. When we read the meniscus, remember a meniscus is this little dip that water forms when in something small like a straw or a graduated cylinder or anything quite thin. We'll see this dip because water pulls itself up the sides a little bit. All right, when I want to measure the volume, I always measure to the bottom of this meniscus here. To measure it, I want to look exactly at eye level at this meniscus. If I'm looking down, if I am holding it lower than my eyes and I'm looking down, it might appear that there's more there than I would have assumed. If I'm looking up, I might get a smaller volume than I would have assumed. So it's really important that we're looking at something square on. Parallax is the idea that by looking from different places, we get different readings. You could see this if you used maybe one of the clear measuring cups in your kitchen and you were pouring something in and you measured from maybe looking at the counter height exactly at eye level, and then just standing up, having that measuring cup on the counter and looking down. You'll see that the measurements are slightly different because your viewpoint has changed. All right, parallax with stars then. What we know is that the longer the baseline we use to measure or for our triangulation calculations, the more accurate the result. The longest baseline that astronomers can actually use is the diameter of Earth's orbit. So we can take measurements 6 months apart to use the full diameter of our orbit. That creates the longest baseline. However, because of this, the appearance of the star in the sky is different. When I'm viewing this star, it's pink here in our little diagram. As I view it in July, we see its position relative to other stars like this. Again, here's the star here. When I view it in January, it appears to be in a different spot. So we need to track this star the whole way through so that we understand that it is still the same star that we're looking at. It's just the frame of reference and the parallax, what is behind it, how we are viewing it, that we see it looks different. Again, looking at our parallax. So Earth in January, and we view this star, it looks like it's kind of overlapping this green one. If we view this in July, it looks like it's between these two stars. So again, it's very important to recognize that they are the same star, it's just the way we are viewing it. The nearer the star, the larger the angle or parallax between these two observations. So the closer it is to us, the more it appears to move based on parallax. The further away, the smaller the movement in the sky, or so it seems. So how far is far? Because space and the universe are so large, we need a large unit of measurement. We're not going to measure in kilometers or centimeters, because it just seems so small in the grand scheme of things. So 1 AU, or an astronomical unit, is the distance that we use. It is the distance from the Earth to the sun. Again, this is an average between the shortest and the longest distance. 1 AU is about 1.496 million kilometers. Sorry, it looks like I've cut off my fun fact there. The nearest star to Earth is Proxima Centauri, and it is about 270,000 AU, or astronomical units, away. So 270 times the distance from Earth to the sun. This is a ginormous amount in kilometers. I think we're into the trillions there. So we want to use a unit that makes more sense for the distances that we're measuring. This was a really great video recently done by Mark Robner, and he used a drone to show the distance between planets and the representative sizes of planets and the sun. I think it's really worth taking a look at. Some practice for topic 4 in your learning guide. There's also, again, some extra practice in your textbook if you're looking for it.